In this video, we will be covering section 7.4 reciprocal functions. I would like you to go onto D2L and print off the notes for section 7.4 so you can follow along. I will be going through the examples and the notes. Feel free to pause the video at any time if you need to write something down, or rewind it if you want to hear something again. When the video is complete, you can watch it again, or you can go on and do the try on your own questions. So let's look at section 7.4, reciprocal functions. Let's begin by talking about what a reciprocal function actually is. Reciprocal function is taking any function y equals to f of x and taking the to examine what happens when f of x is equal to 0 because we can't divide by 0. So what we're going to do, what the definition of a reciprocal really is taking any function that has points x, y, and looking at the corresponding points of the reciprocal. So notice that the x values stay the same, but the y values change because I take the reciprocal, which is 1 over y. Let's look at an example of what a reciprocal function and its corresponding graph look like. So you can see here in this example, I have a linear function, y equals 2x plus 5, and over here I have the reciprocal 1 over 2x plus 5. So you can see those graphs look quite different. Let's look at the corresponding table of values. First thing is, my x values, as we discussed previously, stay the same x values. Those don't change. It's just the y values that change. So let's look at some of these y values just as an example. Let's say if I have a y value of 5, you can see over here I have a y value of 0.2 because 1 divided by 5 is 0.2. If I have a y value of 2, for example, you can see over here 1 divided by 2 is 0.5. So all I'm doing is taking the reciprocal of all of my y values. Let's look at this point here, 1. When I take the reciprocal of 1, I get 1 divided by 1, which is the same. So you can see these points here stay the same. Let's look at what happens here when y is 0. If I take the reciprocal of 0, 1 divided by 0, I get an error message because I can't divide by 0. So if I have an error message there, let's look at what happens with the x value that goes with that. An x value of negative 2.5, if we look on the graph here, I have this dotted line. And this dotted line is actually called an asymptote. And that's something important with reciprocal functions. Let's look at an asymptote. An asymptote is an imaginary line that the graph of a function can approach but never cross or touch. So you can see in these reciprocals I have two asymptotes. On that last example, it was at x equal to negative 2.5, and I have another one at y equal to 0. The reason that I had one here was because negative 2.5 was the x-intercept of the original function, and an x-intercept has a y value of 0, and I can't take the reciprocal of 0. The reason why we have an asymptote here is because there is no possible way of making a y value of 0. If I take the reciprocal of any number, think of any number, if I take the reciprocal of that number, it would be impossible for it to be a value of 0. That's why I have another asymptote at y equal to 0. So let's look at functions and their reciprocals in a little bit more detail. Let's look at some of these important points. So we said the definition of a reciprocal function is where x is going to stay the same, but y becomes the reciprocal. So that's true of every point. So we can look at any point on the function, take the reciprocal of y, and get a point on the reciprocal function. Let's look at a few of these important points, though. We already talked about this when y was 0 for an x-intercept, and we have 1 divided by 0. We can't divide by 0. So this creates a problem. So that means that an x-intercept of a function becomes a vertical asymptote of the reciprocal function. If I have any x value where y is a big value, let's say for example 100, if I take the reciprocal of a big number, I'm going to end up with a small number. So let's look at 100. If I take the reciprocal of 100, I get 0.01. That's a small number. Same thing happens for small numbers. If I have a small number, let's say 0.01, if I take the reciprocal of a small number, I'm going to get a big number because 1 divided by 0.01 is 100. So you can see that it's the opposite. So big numbers on my function become small numbers on my reciprocals. Small numbers on my function become big numbers on my reciprocal. That's going to help us when we come into graph. And then we saw one of the invariant points. When y is 1 and I take the reciprocal of 1, I still end up with 1. So it stays the same. This point x1 on the function still stays as x1 on the reciprocal. The same is true for negative 1. When I have negative 1, 1 divided by negative 1 still stays as negative 1. So because these points stay the same, we call them invariant point, which means unchangeable. So these are called invariant points. They do not change values. Those are also going to help us when we graph. So let's put all of these ideas into play with the following examples. So just to recap some of the tips that we talked about, x-intercepts of the function become vertical asymptotes of the reciprocal. Those are those vertical dotted lines that a graph can come close to but not cross. We talked about horizontal asymptotes. That's that horizontal line at y equal to 0, which is also known as the x-axis. So a reciprocal function will never cross or touch the x-axis. We're always going to look at invariant points when y is positive and negative 1, again because the reciprocal of 1 is 1 and the reciprocal of negative 1 is also negative 1. We're going to look at those big and small points. So if a function is increasing, the reciprocal will be decreasing. The same can be said the other way around. If the function is decreasing, the reciprocal will then be increasing. And then one thing that we didn't mention before that's important is that the sign of a reciprocal doesn't change. So if the function is above the x-axis, it's a positive number, it will also be a positive number when I take the reciprocal. So let's look at an example here. So we have this graph 2x plus 5, and we want to graph the function and its reciprocal. So let's start with these invariant points. So those are the invariant points of y equal to 1 and y equal to negative 1. So let's look at 1 first. So I'm going to substitute y for 1 right here, and I end up with this equation, 1 equals 2x plus 5. So I'm going to subtract 5 from both sides of the equation, and I get negative 4 equals 2x. And then I'm going to divide both sides of x by 2, and I get x equals negative 2. So I have an invariant point at negative 2 and positive 1, which means on the function and the reciprocal function, they will both have that point. Let's look at now when y is negative 1. So again, here I'm going to substitute y for negative 1. So I have negative 1 equals 2x plus 5. So I will subtract 5 from both sides. I get negative 6 equals 2x, and I will divide both sides by 2, and I get that x is equal to negative 3. So my second invariant point is at negative 3 and negative 1. So I have my invariant points. Now let's examine the graph of y equals 2x plus 5. So that is a linear graph. So let's plot these invariant points that we just calculated at negative 2, positive 1, and negative 3, negative 1. Then the next thing that I want to figure out is my x and y intercepts. And again, you can do that on your calculator. And I label those on my graph. I'm now going to use all of this information to come up with the reciprocal function. So I want to graph the reciprocal of this 2x plus 5. I want to graph y equals 1 over 2x plus 5. So the first place I'm going to start is with my x-intercept. So my x-intercept of negative 2.5 means I have a vertical asymptote here at negative 2.5. So I know that the graph can come close to this, but it can't touch it or cross it. Remember that we also have a horizontal asymptote at y equals to 0, which is right at the x-axis. So I've split my graph into 4 little sections here. So the graph can't go across sections. I'm going to now graph my invariant points, which was negative 2 and positive 1. So right there. and -3 and -1. So on either side of the asymptote. I'm also going to graph my y-intercept. So my y-intercept up here of 5, 1 divided by 5 is 0.2. So it's going to be a small number here. Okay, so that's not really enough to graph the graph yet. So let's look up here and let's look at what happens to the right of the x-intercept. Notice to the right of the x-intercept, the y value starts to get big. So y becomes a big number. It goes from small to big. So when I take the reciprocal of a big number, 1 divided by a big number is a small number. So down here to the right of the asymptote, I know I'm going to start big and I'm going to get small like that. Okay, back up on the original function to the left of the x-intercept, I'm getting small. So you can see I'm starting big and I'm getting small. So the opposite is going to happen down here. To the left of the the vertical asymptote, I'm not going to start big and get small. I'm going to start small and get big like this. So this would be the graph of y equals 1 over 2x plus 5. And you can verify that on your graphing calculator. But we just used all the principles to come up with that graph. So let's look at in general what linear graphs are going to look like. So if I start with a linear graph and I take the reciprocal, it's going to be one of these two pieces. Notice that these two pieces are reflections of one another. We have a positive piece and we have a negative piece. Same thing here, reflections of one another. So it's always going to look like that. Now, if I start my original graph with a positive slope, my reflections are going to be like this, from quadrant 1 to quadrant 3. If I have a negative slope of my original function, my reflections are going to be from quadrant 2 to quadrant 4. So that's just a little hint to help you come up with the shape of a linear graph and its reciprocal. Let's now look at what happens when I have a quadratic graph. So, quadratic graphs. So again, I am going to start with my invariant points. But I'm going to do these on the graphing calculator because it's a little bit more complicated. So you can see over here, I've put in my graph y equals x squared minus 4 into y1, and into y2 I'm going to put y equals to 1. And I'm going to use in my calculate menu the intersect, and I have 2 points of intersection that I need to figure out. Okay? Then I'm going to go back into my y equals, and in y2 instead of having positive 1, I'm going to have negative 1, and I calculate those points of intersection as well. So I have 4 invariant points of this graph. So let's look at the graph y equals x squared minus 4. So I already know the invariant points. Next thing I'm going to do is calculate my x-intercepts. And those are important because remember the x-intercepts of a function become the asymptotes of the reciprocal. So I go through and I calculate the x-intercepts to be positive and negative 2. And then I would also like to find my y-intercept, so I use my trace function and I come up with that as my y-intercept. So let's put some of this information in on my graph. So again, I'm going to start with my x-intercepts. So I have 2 x-intercepts, which means I have 2 asymptotes. So I'm going to have an asymptote at 2 and another one at negative 2. And then also remember I have negative 2. There we are. And I also have that asymptote at the x-axis because y cannot equal 0. So now I've split my graph into 6 sections. So let's graph my invariant points. So I have 2.2 and positive 1. I have 1.7 and negative 1. I have negative 1.7 and negative 1, and negative 2.2 and positive 1. Okay, I've got my invariant points. And then let's look at my y-intercept of negative 4. If I take the reciprocal of negative 4, I get negative 1 over 4, which is negative 0.25. So, similar to what I did with my linear graph, let's look at the sections around the x-intercept. So if I look at to the left of the x-intercept, I am starting small and getting big. So I'm starting small and getting big. So to the left of the asymptote here, I'm going to, instead of starting small and getting big, I'm going to start big and get small. Remember, everything is opposite. If I look at this section here to the right of the x-intercept, I'm starting small and getting big. So to the right of the asymptote, instead of starting small and getting big, I'm going to start big and get small, like that. Okay, and then the last section is in between the x-intercepts. So you can see here I'm starting starting big, getting small, and then turning around and coming back. So start small, get big, come back around. So I'm going to do the opposite over here, and it's going to go in this direction here. Okay, so it is the opposite in that middle section. So I know altogether here, this is the graph of 1 over x squared minus 4. And you can verify all of that on the graphing calculator. We have two sections here, the two asymptotes, the horizontal asymptote, and then this middle section here. So let's look at quadratic functions in general. They're in general going to be one of these two formats. So I want you to first of all notice that each of these have mirror images of one another. So they have the one section that are mirror images of one another. And then they have that middle kind of parabola shaped piece here. So if the mirror images are above, the parabola piece is below. If the mirror images are below, the parabola piece is above. So the quadratic functions are going to look something like that. Here's a little hint. If a is a positive value, in other words, it's a quadratic that opens up, when I take the reciprocal, my mirror images will be up and my parabola part will be down. If I have an a value that is negative, in other words, the original graph opens down, my mirror images open down, they're down, and then my quadratic part, my parabola part, is opening up. So that's just a little hint to kind of come up with the shape. So just to end here with one more example, I want to look at what happens when we're going backwards. When we're given a function that is a reciprocal function and we want to figure out the graph of the original function y equals to f of x. So if I look at this reciprocal function here, I have to really decide, is it a quadratic or is it linear? And I can see, because I have these two reflective pieces, I don't have the three sections, I know that y equals f of x must be a linear function. So to come up with a linear function, I just need 2 points. Connect the dots and they are aligned. So let's look at my first point here, 3 and 1/3. I know that my x values stay the same, so this x value is 3. Now I know that I took the reciprocal and it became 1 over 3, so to go backwards, I'll take the reciprocal, so 1 over 3, I take the reciprocal, and it becomes 3 over 1, or just 3. So I know that one of my points on the linear graph is this point 3 and 3. The second piece of information I have is my asymptote, which is passing through the point x equal to 2. So if it's an asymptote of my reciprocal function, it is an x-intercept of my original function. So that's all I need, 2 points. Connect the dots. And that is y equals to f of x of the original function. So that's how to go backwards. So that concludes section 7.4. I'd like you to go back over the notes, listen to any part of the lesson again that you need to, do the try on your own questions, and if you have any further questions, feel free to send me an email with your questions.